Our next unit in AP Chemistry is chemical equilibrium, which is always the first question on the free response calculator portion of the AP exam. So this is actually a very large concept, and you'll actually see it in many, many problems. Equilibrium we have discussed in brief detail in previous units. However, now we are going to be going into it in much greater detail. And from now on, we will most likely have one equilibrium problem on each net ionic quiz. Well, what is equilibrium? Equilibrium is the rate at which the forward reaction equals the rate at which of the reverse reaction. So much like you running on a treadmill. When you're on the treadmill, the rate that it's going backwards equals the rate at which you're going forwards. If you're not, you're going to fly off the treadmill. Or if you're going faster and the treadmill's going backwards, you're going to run into the head bar. So you are at a state of equilibrium. In chemistry, we deal with this in ways of reactions. A reaction is at equilibrium, and a reaction will reach a state of equilibrium. We show this by using a double arrow. So, for example, the Haber process, and this is called the Haber process. It's the formation of ammonium from elemental nitrogen and hydrogen, is a reversible reaction and will reach a state of equilibrium. We can show which side is favored by altering the size of the arrows. If products are favored, you would have a smaller reverse arrow. And if reactants are favored, or through formation of reactants are favored, you have a smaller forward arrow. Systems at equilibrium are said to be dynamic, meaning that they are constantly in motion. At any given moment in the Haber process, nitrogen and hydrogen atoms are colliding to form ammonium. At the same time, ammonium atoms are decomposing to form nitrogen and hydrogen. Just like on the treadmill example, you are constantly in motion on a treadmill in order to stay at equilibrium. Notice that I have made no reference to concentration, and that's because equilibrium has nothing to do with concentration. While it can be affected by concentration, it is not that the reactant's concentration has to equal the product's concentration. This is extremely rare that your reactants and products will equal each other in concentration at equilibrium. In fact, it will almost never occur. It is the rates that matter in equilibrium, which is why we did kinetics before we did equilibrium. If I look at a graph of the concentration of reactants versus the concentration of products per time in a reaction, I would assume that A and B here are my reactants because they are dissipating to form my products, which must be C and D because they are appearing. Concentration decreasing versus concentration appearing. The point at which each line flatlines, the point at which each line begins to flatline, or not begins, the point at which each line has flatlined is the time it takes to reach equilibrium. And this can be signified with a T, a TE, or TEQ. Either one means the same thing. It's the time it takes for the system to reach equilibrium. Now, whether equilibrium lies far to the right, meaning that the production of products is favored, or far to the left, meaning that the production of reactants is favored, is dependent on a couple things. It depends on the initial concentration, because if you have more reactants or more products in solution, you'll have more collisions, and therefore your reaction will occur faster, and therefore rates in one way or another will be affected. The relative energy of the reactants and the products will also help determine to which side equilibrium is found. Because if your reactants have more energy, they'll collide and have more fruitful collisions and therefore produce more products, and the same goes with your products in the reverse. The degree of organization of your reactants and products. Remember that nature favors the production of disorder. And lastly, the value of K. Notice that this is a capital K, not a little k. Little k is rate, it deals with your rate law expression. Capital K is something completely different. And we're going to go into capital K for the rest of this video. So without further ado, K. This lesson is brought to you by the letter K, as in mass action expression. I've already taught this to you at the very beginning of the year, but we are going to go into it in much greater detail now. The law of mass action expression deals with an equilibrium constant, which we symbolize with the capital letter K, which is not to be confused with the lowercase k. Capital letter K, the mass action expression, or the equilibrium constant, is equal to the concentration of products over the concentration of reactant. But there's a lot more to it than that. For right now, for this next concept I'm about to introduce, you need to know that K is proportional to the concentration of products over reactants. So that means that if K is greater than 1, that means that your products have a greater concentration at equilibrium than your reactants. So therefore, the reaction must favor products at equilibrium. You have an improper fraction, so it must be greater than 1. So products must be a larger number than reactants. If K is less than 1, then the reaction favors reactants at equilibrium, which means that you have a true fraction. Products would be you'd have less concentrated products than you would reactants. A mass action expression, or the equilibrium constant expression, can be written by taking the stoichiometric values for a balanced equation and raising the concentrations to each of those values. What does that mean? It means if it's a coefficient, it becomes an exponent, and it's going to be products over reactants. So K, for the Haber process, which remember is this equation here, would be the concentration of ammonium squared, because it has a coefficient of 2, divided by the concentration of nitrogen to the first, because it has a coefficient of 1, times the concentration of hydrogen to the third, or cubed, because it has a coefficient of 3. And we could call this K, because it's the equilibrium constant expression, or we could call it Kc, because it's the equilibrium constant expression for a concentration, thus the bracket. Or, since we're talking about equilibrium, it can also be written as KEQ. Those three are identical. Oh, my equal sign has been trespassed upon my fraction. So K, KEQ, and KC all deal with concentrations. If we're dealing with a gas, we can do what's called KP. So with gases, we can use pressure values here. So atmospheres, or torrs, or millimeters of mercury, or I just had a brain fart and can't remember what the other one was. But if we have pressures, we can use those. However, we will make sure that when we write out our mass action expression, or we write our equilibrium constant, we will not use brackets, because brackets symbolize moles per liter. They cannot be used if I have atmospheres. It does matter. So do not use brackets unless you are using a concentration value. If you're using pressure values, you're going to use parentheses. Also, we could also use partial pressure values, where it simply would change, where we could sub in the partial pressures of ammonium and nitrogen and hydrogen and simply raise them. When you write your equation, your equilibrium constant expression, just make sure you have the right notation. If you're using a pressure, you're either going to use brackets, or you're going to use the partial pressure and write your equation as it's seen here. If you're using concentrations, you'll use brackets. Now, because chemists love to have rules, there are a couple rules that go with mass action expressions and equilibrium constants. Whenever you have a pure solid or liquid, you will not put it in your mass action expression. You will not put it in your equilibrium constant. And because the concentration of these are so large that they will have very little effect on actual equilibrium. Also, anytime you have water, since water is a pure liquid or a pure substance, it also does not appear in the expression. So we only write gases and aqueous solutions. We only write gases in aqueous states of matter in our equilibrium constant expression. Lastly, cue the heavenly music, because all values for an uppercase K have no units. Send out the parade. Or as Beaker would say, me, 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 me. Next slide. So if we're asked to write the mass action expression for the above reaction here, it's actually very simple. Since these are all gases, they're all going to appear. We can't count any of them out. So K equals NO2 to the 4th because it has a coefficient of 4, H2O to the 6th because it has a coefficient of 6, divided by, pardon my brief lapse in formatting, ammonium to the 4th, coefficient of 4, and times oxygen, coefficient of 7, or to the 7th because the coefficient to the 7th. So we could say that that's our Kc or Keq. If we were given pressure values, we could do the same thing. It would just simply be, instead of brackets, we would have parentheses, and we would say that's our Kp because we're doing pressure values. Or we could also have the partial pressure. So the partial pressure of nitrogen to the 4th times the partial pressure of water to the 6th, so on and so forth. And if we were given those values, we would simply plug them in and solve for a numerical number for K, which, again, hallelujah, would have no units. All right, so what happens if you change the stoichiometry of a problem? So let's say that you instead double the stoichiometric coefficients of everything. What would that do to K? Well, mathematically, it would cause the value of K to square. If we tripled the stoichiometric volumes of everything, it would cause K to cube. So the general rule, not general, but the rule is that if whatever you do to the stoichiometry, so if I multiply stoichiometry by 1/2, the value of K is to the 1/2. Or if I double the stoichiometry, 2 times the overall reaction, means that the value of K is squared. If we're asked to give the value of K for the reverse reaction, it's simply the inverse of K, because remember, it's products over reactants. If we reverse the reaction so that our products are now our reactants, it's going to inverse our K. So it would be K to the -1. If we add equations, so we have multiple equations, we're simply going to multiply the K's. So K, the first K times the second K times the third K times fourth K times fifth K times sixth K. So we're asked to calculate K for the Haber process, which remember is the formation of ammonium. And we're giving concentrations. If you're doing this at home, this is problem number 3, or exercise 3 in your notes. You can, there's a typo. This should say 3.1 in your note, in your packet. In your notes, it looks like it says 31. It should say 3.1. All right, so calculate the value of K. We have to write our expression for this. So these are all gases, and we have concentrations for them, so we can go ahead and do that. So I know that this is the equilibrium expression constant, or equilibrium constant expression. I would recommend, and highly, highly recommend, that you always start a problem by, or always start an equilibrium problem by writing the expression. Because often this would be 1 point in of itself, free of everything else. If you skipped over writing K equals and all this, you would have forfeited 1 point on this problem. So now that I have this, I can plug in these values here. Do a little bit of plugging and chugging on my calculator, and I find that K equals 3.8 times 10 to the 4th. Next, we're asked to calculate the equilibrium constant for the reverse reaction. It's going this way when we calculate it. Now look at it, it's going backwards. So this is simply, let's call this K prime for lack of a better definition. In the reverse reaction, this K would equal the inverse of K prime. So I take this value and put it to the -1, and I find that K equals 2.6 times 10 to the minus 5. Lastly, they've halved all of the reaction. So if we take this K and take the square root of it, or raise it to the 1/2, we would find the K for that value.